In this video, we are going to build an AI-powered video search engine using Python, OpenCLIP, FAISS and Streamlit. So let's start with a quick demo. I have a collection of videos stored inside a folder, and let's say I am trying to find a video that contains people playing football. So instead of manually opening each video and searching through them one by one, I can simply type playing football in the search box. As you can see, the application instantly returns the most relevant video. It also shows the exact frame where the match was found. If I click the play button, the video opens and automatically jumps to the relevant timestamp where the football scene appears. Let's try another example. This time I will search for eating food. Again, the application analyzes the meaning of the query and finds the most relevant video from the collection. We can immediately preview the result and jump directly to the matching moment in the video. Now let's try more specific term, eggs. Even though I am searching with a single word, the AI is able to understand the visual content of the videos and locate the frames that contains eggs. Here you can see the matching video. We can build this application with OpenCLIP and FAISS library without using any external API keys. Now let's understand how this application works behind the scenes. The process begins with indexing the videos. First, the application scans all the videos available in the specific folder. Before we can search videos, we first need to understand what is inside them. A video is made up of thousands of individual frames. Processing every single frame would be expensive and slow. Instead, we sample frames at regular intervals. In this project, we extract one frame every 2 seconds using OpenCV. Think of these frames as snapshots that summarize the video content over time. Once these frames are extracted, they are processed by OpenCLIP. OpenCLIP converts each frame into a numerical representation known as embedding. Rather than focusing on individual pixels, these embeddings capture the semantic meaning of the image, allowing the system to understand the content at a higher level. After generating the embeddings, they are stored in a FAISS index. FAISS is a high-performance similarity search library that enables fast and efficient searching across thousands of embeddings. Along with the embeddings, we also store metadata such as the video path, timestamp, thumbnail image, and video duration. This metadata helps us to identify and display the correct video when a match is found. When a user enters a search query, OpenCLIP processes the text and converts into an embedding using the same semantic space as the image embeddings. This allows text and images to be compared directly based on their meanings. Once the text embedding is generated, it is searched against the FAISS index. Since both the text and video frames are represented in the same semantic embedding space, FAISS can quickly identify the frames that are most similar to the user's query. The search returns the closest matching video frames along with their similarity scores. For each matching frame, the application retrieves the associated metadata that was stored during indexing, such as the video file path, thumbnail image, timestamp, and video duration. The results are then displayed in a Streamlit interface, where users can see preview thumbnails of the matching videos, the exact timestamp where the match was found, and the relevance score. Now let's go through the code. I am not going to explain every line. Instead, I will focus on the important methods and the key concepts used in this application. Here, we have two main files, app.py and helper.py. I will start with the helper.py because this is where all the indexing happens. Think of this file as the component that prepares our videos for search. The first important section is the loading the OpenCLIP model. OpenCLIP is the AI model that understands both images and text. Later, when a user searches using natural language, OpenCLIP helps us compare that text with video frames. Next, we have build video index function. This function is responsible for scanning videos, extracting frames, generating embeddings, and building the FAISS index. The first thing it does is find all supported video files inside the selected folder. This allows the application to process multiple videos automatically instead of handling them one by one. After that, we start reading each video using OpenCV. Rather than processing every single frame, we extract one frame every 2 seconds. This makes indexing much faster while still capturing the overall content of the video. There is a constant in the script, frame interval second. We can change this value if you want to. For example, if a video is 30 fps, if you give 2 seconds, it will extract one frame every 60 frames. If you increase this value, the indexing may be faster, but there are chances to miss some events in the video. Once a frame is extracted, we convert it into an embedding using OpenCLIP. This is one of the most important steps in the entire application. Instead of storing raw image pixels, we store the semantic meaning of the frame. We then normalize the embedding. This ensures all embeddings have the same length, which improves similarity search accuracy. Next, we save the thumbnail for the extracted frame. These thumbnails are later displayed in the search results inside the Streamlit application. Along with the embeddings, we also store metadata. The metadata contains information such as video path, video name, timestamp, duration, and thumbnail location. This helps us identify exactly where a matching frame came from. Once all video have been processed, we create a FAISS index. FAISS is the vector database used in this project. It allows us to perform very fast similarity searches across thousands of video frames. We then add all embeddings to the FAISS index. At this point, all video content becomes searchable. Finally, we save both FAISS index and the metadata. This means we only need to index the video once. Later, our application can simply load the saved index and immediately start searching. Now we can check the app.py. This function loads the OpenCLIP model and tokenizer. The model is used to convert user search queries into embeddings that can be compared with video frame embedding stored in FAISS. Cache resource decorator ensures that the model is loaded only once, which makes the application faster. This function loads two files created during indexing. The FAISS index containing all the frame embeddings, the metadata file containing video path, timestamp, duration, and thumbnails. Without these files, the application cannot perform searches. Build video index. When the user clicks index videos, this function is called. It scans all the videos in the selected folder, extracts frames, generates embeddings using OpenCLIP, and stores everything in the FAISS index. This is the step that makes video searchable. This slider acts as a quality filter. Lower values return more results, higher values return only stronger matches. This gives users control over how strict the search should be. When a user enters a search query, OpenCLIP converts that text into an embedding. Because OpenCLIP uses the same embedding space for both images and text, we can directly compare text queries with video frames. This is where the actual search happens. FAISS compares the query embedding against all stored frame embeddings and returns the most similar matches. This process is extremely fast even when thousands of frames have been indexed. When the user clicks play, the application opens the video and automatically jumps to the timestamp where the match was found. This is one of the most useful features because users don't need to manually search through the video. Now let's set up the application. First, open a terminal or command prompt and clone the repository from GitHub. Next, move into the project folder. Now let's install all the required Python packages. This will install Streamlit, OpenCLIP, FAISS, OpenCV, PyTorch, and all other dependencies needed by the application. If you are using NVIDIA GPU and want faster indexing performance, I recommend installing the CUDA version of PyTorch. you can find the latest installation command on the official PyTorch website. Once the installation is complete, we can start the application using Streamlit. After a few seconds, Streamlit will automatically open the application in your browser. So here, we can provide the folder path that contains the videos we want to search. Once we provide the folder path, we need to build a vector index. This index is what enables the search functionality. I am currently using a folder that contains 10 videos. Now I will click the Index Videos button to start building the vector index. So keep in mind that this process will take some time depending on the number of videos that you have. I am currently running the CPU version of this application, so the indexing process takes a bit longer. If you have GPU available, indexing can be significantly faster. Another factor that affects indexing time is the frame extraction interval. Right now we are extracting and indexing one frame every 2 seconds. You can increase this value to 3 seconds, 5 seconds or even higher to reduce the number of frames being processed. This will make indexing faster and require less storage. However, there is a trade-off. Since fewer frames are analyzed, the application may miss some important scenes, which can slightly reduce search accuracy. You can see the progress of the current indexing here. Once the indexing is complete, we can start searching the videos. So we don't need to build the index every time you open the application. After the index is created and saved, you can search the videos whenever you want. You only need to rebuild the index if you add new videos to the folder. Now let's try a search. Suppose I remember that one of the videos contains a red car, but I don't remember the file name. So instead of manually checking every video, I can simply search for red car. As you can see, the application finds the matching result. When I click the play button below the thumbnail, it opens the corresponding video and automatically jumps to the timestamp where the red car was found. In this case, the match was found at around 8 seconds. If I play the video, you can clearly see the red car. We also get the full file path of the video. Let's try another query. 2-person cycling. Again, the application successfully finds a matching video. Here, the relevant scenes appears at around 14 seconds, where 2 people are cycling. Let's try a few more examples. Now let's talk about similarity threshold. The similarity threshold controls how closely a video frame must match the search query before it appears in the results. A lower threshold returns more results, including weaker matches. A higher threshold returns fewer results, but the results are usually more accurate and relevant. For example, in the surfing search, the threshold is currently set to 0.20. And we can see 4 matching results. If I increase the threshold to 0.30, only the strongest match remains because the weaker matches are filtered out. So you can think of the similarity threshold as a quality filter. Lower values show more results, while higher values show only the most confident matches. And finally, as I mentioned earlier, you don't need to rebuild the vector index every time you use the application. Once the index has been created, you can continue searching for videos whenever you want. Re-indexing is only required when new videos are added to the folder. I will include the complete source code and project link in the description below. Feel free to check it out. So that's all for today's video. If you found it helpful, please consider supporting the channel. Thank you for watching and see you in the next video. Bye.